Hello there, and welcome to Sleepy Science. Airplanes may seem complex, but they are designed around one simple goal: predictability. Nothing on a commercial aircraft is left to chance, improvisation, or instinct. Every sound, movement, and procedure follows rules that have been tested repeatedly under controlled conditions. Flying works not because pilots react quickly, but because systems are built to behave the same way every time. Once you understand how routine and controlled this process actually is, the experience of flying becomes much easier to relax into. Commercial airplanes are certified to fly safely even if one engine fails completely, and this is not a rare or optional rule. Before an aircraft is allowed to carry passengers, it must prove that it can take off, climb, cruise, and land safely with one engine not working. Engineers assume engine failure will happen and design the plane around that idea. Pilots are trained again and again to handle this situation calmly and step by step. The remaining engine is powerful enough to keep the aircraft flying normally and reach a safe airport. In fact, planes regularly practice this condition during test flights. What often surprises people is that many flights have landed safely with one engine shut down, and passengers never even noticed. This rule exists so that flying never depends on a single part working perfectly. The aircraft is always prepared for something to stop working, and that preparation is what makes flight feel routine and controlled. Modern jet engines are built to run continuously for thousands of hours without being shut down, and they are designed for steady operation rather than stress. These engines are tested on the ground at conditions much harder than normal flight, including extreme heat, cold, and long running times. During daily operations, engines usually work far below their maximum limits, which helps them last longer. Sensors inside the engine constantly check temperature, pressure, and rotation speed. If something begins to change, maintenance teams see the data early and inspect the engine before it becomes a problem. What makes this calming is that engines are not pushed to their edge during flight. They are built to operate smoothly for long periods, often flying several routes a day without issues. The goal is not speed or excitement, but consistency. Because of this design, engine behavior is predictable, quiet, and stable for most of the flight. Airplane wings are designed to bend several meters upward without breaking, and this bending is actually a sign that the wing is working correctly. Wings are not meant to stay stiff. Instead, they are built to be flexible, so they can absorb forces from air movement, turns, and changes in speed. During certification tests, manufacturers bend wings far beyond what they will ever experience in real flight. These tests push the wing until it reaches extreme angles, proving it can handle stress safely. When you see a wing flex during turbulence, it is not losing control. It is adjusting naturally to the air. This flexibility reduces pressure on the aircraft structure and keeps the ride smoother. The wing shape spreads forces evenly across its surface, which prevents sudden damage. Knowing that wings are designed to bend on purpose helps explain why airplanes remain stable even when the air is not perfectly smooth. Pilots do not manually fly the plane for most of the cruise phase, and this is done to increase safety, not reduce control. Once the aircraft reaches cruising altitude, autopilot systems manage speed, direction, and altitude with extreme precision. These systems can make tiny adjustments faster and more accurately than a human hand. Pilots remain fully responsible and closely monitor everything, but they allow the automation to handle routine control. This reduces fatigue and helps pilots stay alert for important decisions. Autopilot does not mean the plane is flying on its own without supervision. It follows inputs chosen by the pilots and approved flight plans. If needed, Pilots can take manual control instantly. What is interesting is that most flights feel smooth because computers are constantly correcting small changes that passengers never notice. This quiet teamwork between pilots and systems is one reason long flights feel steady and calm. Autopilot systems can control pitch, roll, speed, and altitude at the same time, and this is one of the main reasons flights feel smooth and steady. Pitch controls whether the nose points up or down. Roll controls how the plane tilts left or right. Speed controls how fast the aircraft moves through the air. And altitude keeps the plane at a fixed height. The autopilot constantly watches all of these at once using sensors placed around the aircraft. It makes small corrections many times each second, far faster than a human could react. Pilots program the autopilot with clear limits and targets, and the system follows them precisely. If wind changes or air pressure shifts, the autopilot adjusts gently instead of suddenly. This prevents sharp movements that passengers might feel. The important thing to know is that autopilot does not make big decisions. It handles routine control, so pilots can focus on monitoring the flight and planning ahead. The air inside an airplane cabin is refreshed every few minutes, which often surprises people who think the air is reused for long periods. Fresh air is taken in from outside the aircraft at high altitude, where it is clean and low in pollution. This air is compressed, cooled, and then mixed with filtered cabin air before entering the cabin. As new air comes in, old air leaves the aircraft through controlled exit valves. This constant flow means the air you breathe is not sitting still. It is always moving and being replaced. The system is designed this way to keep oxygen levels stable and remove odors and particles. Even during long flights, the cabin air does not become stale. What makes this calming is that the airflow is gentle and continuous, not sudden or strong. This steady replacement of air helps maintain a comfortable environment and supports passenger comfort throughout the flight. Cabin air is passed through HEPA filters similar to those used in hospitals, and these filters play a quiet but important role during flight. HEPA filters are designed to capture very small particles, including dust, pollen, and many types of airborne germs. As cabin air is circulated, it passes through these filters before being mixed with fresh air and returned to the cabin. This process happens again and again during the flight. The filters are highly efficient and are replaced or cleaned regularly as part of maintenance schedules. What makes this system effective is that the air flows vertically, entering from above and exiting near the floor. This reduces how far particles can travel sideways. Many people are surprised to learn that airplane cabin air can be cleaner than air in crowded indoor spaces. The filtering system works quietly in the background, helping keep the air clear without passengers ever noticing it. Airplanes are tested under loads far greater than they experience in real flights, and this testing happens long before passengers ever step on board. Engineers apply extreme forces to wings, fuselage sections, and landing gear to see how they respond. These tests push parts well beyond normal limits, sometimes until they bend heavily or even fail. The goal is to understand exactly how much stress the aircraft can handle and where its limits are. During real flights, the forces are much lower than what was used in testing. This creates a wide safety margin built into every flight. Turbulence, turns, and landings all stay within these tested limits. What makes this reassuring is that airplanes are not designed just to meet requirements, but to exceed them. By proving strength under extreme conditions, engineers ensure that everyday flying stays well within safe and controlled boundaries. Every commercial flight is planned with multiple alternate airports, and this planning happens before the plane ever leaves the gate. Pilots and dispatchers study the route, weather, and traffic conditions, and then select backup airports along the way. These alternates are chosen based on runway length, weather forecasts, fuel needs, and available services. If the destination airport becomes unavailable due to weather, traffic, or another issue, the flight already knows exactly where to go. This means decisions are not made in a rush while flying. Everything is prepared calmly in advance. Pilots review these alternates during pre-flight briefings, and they stay aware of them throughout the flight. What often surprises people is that most flights never need to use these airports, but they are always ready. This planning removes uncertainty from the journey. Knowing there is always another safe place to land helps make flying a controlled and predictable process. Fuel calculations always include reserve fuel that often goes unused, and this extra fuel is required by strict rules. Airlines do not plan flights with just enough fuel to reach the destination. Instead, fuel planning includes fuel for the trip, fuel for delays, fuel to reach an alternate airport, and additional reserve fuel beyond that. This means the plane usually lands with a significant amount of fuel still on board. Pilots monitor fuel levels continuously and compare them with planned values during the flight. If fuel use changes due to wind or routing, they already have a margin built in. What is calming about this system is that fuel planning assumes delays will happen. Even when everything goes smoothly, the extra fuel remains as a backup. This approach ensures that fuel concerns rarely become urgent. The goal is not efficiency at the edge, but comfort within safe limits. Jet fuel is less flammable than gasoline at normal temperatures, which makes it safer to handle and store. Unlike gasoline, jet fuel does not easily ignite unless it is heated to a much higher temperature. This property is important because airplanes operate in many environments, from very cold altitudes to warm ground conditions. Jet fuel is designed to remain stable and predictable across these changes. During normal operations, it does not produce dangerous vapors easily. This reduces fire risk during fueling, flight, and maintenance. What many people do not realize is that jet fuel can even be exposed to open air without immediately catching fire. This does not mean it cannot burn, but it means it requires specific conditions to ignite. Engineers choose this fuel because it behaves consistently and safely. Its controlled flammability adds another quiet layer of protection to everyday flying. Aircraft tires are filled with nitrogen instead of air, and this choice is made for safety and reliability. Nitrogen is dry and does not contain moisture, unlike regular air. Moisture inside a tire can expand when heated during landing, which increases pressure unevenly. Nitrogen reduces this risk and keeps pressure more stable. Aircraft tires experience extreme stress during landing, including high speed, heavy weight, and sudden heat from braking. Using nitrogen helps the tire handle these conditions more evenly. Another reason is that nitrogen does not support combustion the way oxygen does. This lowers fire risk if brakes become very hot. Tires are also checked and maintained carefully between flights. What makes this detail interesting is that something as simple as the gas inside a tire is chosen with long-term safety in mind. Small choices like this quietly support the stability of every landing. Airplane tires are designed to withstand extreme heat during landing, which is much higher than what car tires experience. When a plane touches down, it is moving at hundreds of kilometers per hour, and the brakes create intense friction that quickly heats the wheels. The tires must absorb this heat while supporting the full weight of the aircraft, which can be hundreds of tons. They are made from layers of strong rubber and reinforcing materials that can handle repeated cycles of extreme pressure and temperature. Engineers test these tires extensively to make sure they do not fail under stress. Even during multiple landings in a row, the tires maintain their strength. What is surprising to many passengers is that the tires flex and slightly flatten under the load, but this is normal and safe. The heat and pressure are anticipated and accounted for in design. This careful engineering is one reason landings are safe and predictable. Cockpit checklists are used even by very experienced pilots because human memory is not perfect, especially under pressure. Each checklist covers critical systems like engines, navigation, fuel, and emergency equipment. Pilots go through these items step by step before takeoff, during flight, and before landing. The process ensures that nothing is forgotten, even in routine flights. Even pilots who have flown for decades follow the same checklist every time. This repetition might seem unnecessary, but it reduces the chance of mistakes. Checklists are carefully designed to be simple, clear, and logical. Some include reminders for conditions that rarely happen, but could be critical if they occur. By relying on checklists, pilots maintain a high level of consistency and safety. For passengers, this means that many small risks are addressed long before they become noticeable. Following checklists is one of the quiet ways aviation remains so reliable. Pilots train regularly in simulators that recreate rare emergencies, including engine failure, sudden weather changes, or instrument malfunctions. These simulators are realistic enough to make the pilots feel as though they are in a real aircraft. Training this way allows pilots to practice situations they would rarely see in real life, so they remain prepared without endangering passengers. The simulators can speed up, slow down, or repeat scenarios until the pilots respond correctly every time. Pilots learn to follow procedures, make decisions calmly, and use systems effectively during emergencies. Repeating these drills builds muscle memory and confidence. What is calming for passengers is that when unusual events occur, pilots have already practiced them many times. This preparation ensures that most flights remain smooth and predictable. Even situations that sound dangerous are handled methodically because of simulator training. Most turbulence does not affect the structural safety of the aircraft, even though it can feel sudden or unsettling to passengers. Airplanes are designed to flex and absorb the forces caused by uneven air movement. Wings, fuselage, and control surfaces all handle these forces without damage. Engineers perform stress tests on aircraft structures under extreme simulated turbulence, far stronger than what occurs naturally. During a flight, turbulence often causes minor movements, like bumps or shaking, which are uncomfortable but not dangerous. Pilots anticipate turbulence using weather reports and radar, and adjust altitude or speed to make the ride smoother. The aircraft's design spreads forces evenly across its frame, preventing any weak points from being overloaded. Understanding this makes turbulence less worrying. The plane is built to cope with it quietly, so most turbulence is simply a normal, safe part of the flight experience. Air traffic controllers keep large distances between airplanes to prevent collisions and ensure smooth traffic flow. They monitor hundreds of flights at the same time using radar and communication systems. Aircraft are assigned specific altitudes, headings, and speeds so that each plane stays in its own space. These distances are much larger than they appear to passengers because the sky is three-dimensional and there is plenty of room to separate flights. Controllers constantly adjust spacing if weather, traffic, or emergencies arise, making small changes to maintain safety. Even though it might look crowded from inside the cabin, airplanes are rarely at risk of coming too close. Maintaining these distances is a quiet, precise system working behind the scenes. Knowing that every flight is constantly monitored with exact spacing helps explain why flying is remarkably safe and why passengers almost never notice the complexity managing the skies. Planes fly on specific air routes, similar to invisible highways, which are carefully designed for efficiency and safety. These routes are mapped in advance and consider terrain, air traffic, and communication coverage. Pilots follow these routes precisely, using navigation systems and air traffic instructions to stay on course. The routes connect airports through a network of waypoints, which are like checkpoints in the sky. Even when pilots adjust altitude or speed for weather, they usually stay on these planned paths. Following structured routes reduces the chance of mid-air conflicts and makes it easier for controllers to manage airspace. Many passengers are unaware that the smooth, straight path they see outside the window is guided by detailed planning. These invisible highways make flying predictable and controlled. By sticking to them, airlines ensure efficiency, safety, and reliability throughout every flight, no matter the weather or destination. Flight paths are monitored continuously from the ground to track every aircraft's exact position. Radar, satellite systems, and communication links provide live updates to air traffic controllers and airline operations centers. Controllers can see where every plane is, its altitude, speed, and direction, and they can communicate instantly with pilots. Airlines also track flights to make sure they stay on their planned route and can adjust for weather or traffic changes if needed. Even when nothing seems unusual, monitoring continues so that any problem can be addressed immediately. This continuous observation creates a safety net that passengers rarely notice. It also allows airlines to optimize routes for efficiency and fuel savings. The fact that flights are watched constantly explains why airplanes can follow precise schedules safely. Every movement in the air is coordinated quietly in the background, maintaining order across crowded skies. Aircraft systems record data even when nothing unusual happens, and this information is used to maintain safety and reliability. Every flight generates thousands of data points from engines, navigation instruments, control systems, and environmental sensors. This data is stored on board and transmitted to airline maintenance teams. Engineers review it to check for small changes that could indicate wear or potential issues before they become problems. Recording normal operations allows airlines to compare trends over time and predict maintenance needs. Pilots also rely on this data for performance reports and system monitoring. What is surprising is that the plane is always listening to itself, even during routine flights, without passengers noticing. This constant recording is one of the quietest safety measures in aviation. By monitoring everything continuously, aircraft remain reliable, predictable, and ready for almost any condition. Commercial airplanes are inspected after a certain number of flight hours, and this schedule is strictly regulated to ensure safety. Airlines track exactly how long each aircraft has flown, including total hours in the air and the number of takeoffs and landings, because these actions stress the aircraft differently. Inspections can range from simple visual checks to detailed examinations of mechanical and electronic systems. These scheduled inspections help detect wear, corrosion, or other issues before they become dangerous. Even small signs of wear are taken seriously. Maintenance teams follow step-by-step procedures to ensure nothing is overlooked. These inspections are not only for safety, but also for long-term reliability, keeping airplanes in predictable and controlled condition for decades. Passengers rarely notice this process because it happens quietly, often overnight or during short ground stops. But it is one of the key reasons commercial aviation remains one of the safest ways to travel. Some inspections require partial disassembly of the aircraft, meaning engineers take apart certain sections to check internal structures and systems. This can include removing panels, opening access doors, or examining internal wiring, hydraulics, and fuel lines. Engineers do this because not every problem is visible from the outside. Internal inspections reveal cracks, corrosion, or wear that could affect safety if left unnoticed. Even though it seems extreme, these procedures are planned carefully and follow detailed manuals. Special tools and trained technicians ensure the work is precise and controlled. Aircraft are designed so disassembly can be done safely without damaging other parts. What is interesting is that these inspections happen regularly as part of routine maintenance, not only after a problem occurs. This proactive approach ensures that planes continue to operate smoothly and safely every day, maintaining confidence for both pilots and passengers. Airplane fuselages are designed to handle repeated pressurization cycles, which occur every time a plane climbs to high altitude and returns to lower altitude. The pressure inside the cabin is higher than outside air at cruising altitude, so the fuselage experiences a slight stretching and contracting each flight. Engineers account for this in the design, using materials that can flex safely without weakening over time. Tests simulate thousands of these cycles before the aircraft is certified to fly. This repeated movement is normal and expected. It prevents stress from accumulating unexpectedly and keeps the plane structurally strong. Understanding this helps explain why airplanes remain safe even after decades of flights. Passengers may feel slight changes in ear pressure during ascent and descent, but the fuselage itself is engineered to manage these changes quietly and safely, making the cabin environment predictable and controlled. Airplane windows are made of multiple layers of strong materials, and this design helps protect passengers while maintaining visibility. Each window has at least 2 or 3 layers, including an inner pane that passengers touch and outer layers that face the outside. The layers are made from materials that resist cracking, impacts, and changes in pressure. The outer layer is especially strong because it has to withstand high-speed air, debris, and pressure differences between the cabin and the outside air. Engineers test these windows under extreme conditions, including sudden impacts and temperature changes, to ensure they remain intact. Even if one layer were to fail, the other layers maintain safety. What many people do not realize is that windows also help regulate cabin pressure and insulation. This multi-layer design allows passengers to look outside safely without worrying about high altitudes or rapid changes in air pressure. It is a quiet but essential part of the airplane's overall safety system. The small hole in airplane windows, often called the breather or bleed hole, helps control cabin pressure. Airplanes fly at high altitudes where outside air is very thin, so the cabin is pressurized to keep passengers comfortable. The small hole allows air to move between the layers of the window slowly, equalizing pressure and preventing the outer layer from bearing all the stress. Without this hole, the window could experience uneven pressure, increasing the risk of cracking over time. The design ensures that even as the plane climbs or descends, the forces on the window remain balanced. This small, almost invisible feature is carefully calculated by engineers to work with the plane's pressurization system. Passengers rarely notice it, but it is essential for safety. Understanding the function of this tiny hole highlights how even small details in aircraft design contribute to predictable, controlled, and safe flight. Most commercial aircraft can land safely without engine power, and this is because airplanes are designed to glide efficiently. Even if both engines were to stop, the wings continue to generate lift, allowing the plane to descend gradually and maintain control. Pilots are trained to manage the glide, adjusting speed and direction to reach a safe landing spot. The flight instruments and control systems still work during this situation, providing guidance for speed, altitude, and navigation. The aircraft's design spreads forces evenly across the wings and body, so structural safety is not compromised during the glide. While engine power is preferred, it is not essential for a safe landing in most cases. What makes this fact reassuring is that the scenario is extremely rare, but it is prepared for. Pilots know exactly what to do, and the plane itself is engineered to handle the situation, ensuring passengers remain safe. Pilots practice powerless landings in simulators so they are prepared for very rare emergencies. These training exercises replicate conditions where engines fail or cannot provide thrust, and pilots must manage the glide carefully. The simulator allows repeated practice without risk, teaching pilots how to judge speed, approach angle, and touchdown precisely. Pilots learn to prioritize control over speed or altitude, using only the aircraft's aerodynamics and remaining systems. This training builds confidence and muscle memory, ensuring that if an actual engine failure occurs, pilots can respond calmly and correctly. Even though most flights never encounter such emergencies, this practice is routine. Passengers can remain relaxed knowing that pilots have rehearsed these extreme situations multiple times. Simulators are highly realistic, providing visual, instrument, and motion feedback, so pilots gain practical experience. This preparation is part of the quiet system of safety that makes commercial aviation so reliable. The cabin is pressurized to feel like a mountain elevation, not sea level, which keeps passengers comfortable while flying at high altitudes. Air outside the plane at cruising height is too thin for humans to breathe normally. By pressurizing the cabin, the aircraft maintains an oxygen level and air pressure that is safe and tolerable, usually equivalent to 6,000 to 8,000 feet above sea level. This pressure allows passengers to breathe easily, prevents dizziness, and reduces fatigue. The system adjusts slowly during ascent and descent, so the change in pressure is gradual, giving your body time to adapt. Engineers design the cabin structure to withstand this pressure consistently and safely for every flight. Cabin pressurization is monitored constantly by sensors and controlled automatically by onboard systems. Knowing this explains why flying feels comfortable despite being far above the ground. The controlled pressure is another invisible safety feature that passengers rarely notice. Weather radar allows pilots to see storms far ahead and make decisions to keep the flight smooth and safe. These radar systems detect precipitation, clouds, and turbulence by sending signals that bounce back from water droplets and particles in the air. Pilots can see the size, intensity, and location of storms even hundreds of kilometers away. This information helps them choose the safest and most comfortable route, avoiding dangerous weather while maintaining efficiency. The radar updates continuously, providing real-time images that guide flight adjustments. By watching the radar, pilots can also warn air traffic control if a severe storm might affect other aircraft. Many passengers do not realize that when a plane changes course slightly, it is often based on radar readings. This technology allows pilots to plan ahead calmly, reducing sudden jolts from turbulence. Weather radar is an invisible tool that quietly protects every flight. Flights often change altitude to avoid rough air, which helps maintain a smoother ride for passengers. Turbulence usually occurs in layers of air moving at different speeds, temperatures, or directions. By climbing or descending a few thousand feet, pilots can move into a more stable layer with less turbulence. Air traffic control coordinates these altitude changes to ensure there is still enough space between planes. Pilots decide on the best altitude based on weather reports, radar, and experience from other flights on the same route. These adjustments are usually gradual and rarely noticeable to passengers. Changing altitude also helps improve fuel efficiency, as different heights offer varying air density and wind conditions. What is calming about this is that turbulence is managed predictably, not left to chance. Passengers experience less shaking, and the aircraft continues to operate well within its designed limits, keeping the flight smooth and controlled. The cruising altitude is chosen for efficiency and smooth airflow, and this is a key reason long flights feel calm. At higher altitudes, the air is thinner, which reduces drag on the airplane and allows it to use less fuel while maintaining speed. Choosing the right altitude also avoids turbulence from weather systems and rising thermals. Pilots select an altitude based on aircraft weight, temperature, wind conditions, and the efficiency of engines at that height. Air traffic control ensures that different planes maintain proper vertical separation to prevent conflicts. Once the aircraft reaches cruising altitude, autopilot systems maintain it precisely with minor adjustments for air currents. Flying at this optimized height reduces engine strain, smooths airflow over wings, and keeps passengers more comfortable. Understanding that altitude is carefully calculated shows how routine and predictable commercial flights are. Every adjustment is made to balance safety, fuel efficiency, and passenger comfort. Jet engines perform better at high altitudes because the air is thinner, colder, and more stable. Thin air reduces resistance against the moving parts of the engine and the airplane itself, allowing higher speeds with lower fuel consumption. Cold air is denser in oxygen, which improves combustion efficiency while preventing overheating. Engines are designed to operate optimally at the pressures and temperatures found at cruising altitudes. Pilots rely on this advantage to reach destinations efficiently and safely. High-altitude flight also reduces exposure to storms, turbulence, and other obstacles closer to the ground. Even if the engines were capable of lower-altitude operation, the plane would use more fuel and encounter more disturbances. What many people do not realize is that the smoothness and quiet hum of cruising flight are a direct result of this high-altitude performance. The design of engines and flight paths work together to create a controlled and comfortable experience. Airplanes are designed to be naturally stable in the air, which means they tend to return to level flight without constant pilot input. Engineers shape the wings, tail, and fuselage to balance forces and keep the plane from tipping, rolling, or pitching too quickly. This stability makes flying predictable and reduces the workload for pilots. Even when minor turbulence occurs, the plane's natural design helps it stay steady. This does not eliminate the need for pilot control, but it creates a built-in safety feature. The stability is tested extensively in wind tunnels and simulations to ensure the plane behaves as expected in different conditions. Passengers rarely notice this feature, but it contributes to smooth, calm flights. Knowing that the aircraft itself resists sudden changes in movement helps explain why flying feels steady, even at high speeds and altitudes. The plane is engineered to naturally maintain balance, providing both safety and comfort. Control systems are built to prevent extreme pilot inputs, which protects the aircraft and passengers from dangerous maneuvers. Pilots have full authority over the plane, but the systems limit sudden or excessive movements that could stress the airframe. These safeguards, sometimes called control limits, are carefully calibrated based on the aircraft's design and performance. They allow normal adjustments for turns, climbs, and descents, but prevent actions that could cause structural problems. The systems also help reduce abrupt motions during turbulence, smoothing out what the passengers feel. Even experienced pilots rely on these limits because human reflexes can sometimes overreact. By quietly managing extreme inputs, the plane operates within safe parameters at all times. This safety feature is one reason long flights can feel calm even during minor disturbances. The aircraft itself contributes to maintaining stability, ensuring that all maneuvers remain controlled and predictable. Modern planes use computers to smooth control movements, and these computers constantly adjust ailerons, rudders, and elevators to keep flight steady. When a pilot moves a control slightly, the system interprets the input and applies it gradually, preventing sudden jolts. The computer also reacts to changing air conditions, like turbulence or wind gusts, making tiny corrections faster than a human could. This means passengers experience fewer abrupt movements, even when the plane encounters rough air. The system continuously monitors flight data to ensure that control surfaces move correctly and within safe limits. By combining pilot commands with automated adjustments, the aircraft maintains smooth motion and balanced flight. Passengers often notice the plane gliding quietly through the air, not realizing that computers are coordinating countless small corrections every second. This integration of technology increases both safety and comfort, making high-speed travel feel calm and controlled. Aircraft sensors constantly compare data to detect inconsistencies, ensuring all systems operate correctly. Sensors monitor speed, altitude, engine performance, temperature, and more. The computer compares readings from multiple sensors to check for errors or unusual changes. If one sensor reports a value that conflicts with others, the system alerts pilots and adjusts controls as needed. This redundancy ensures that incorrect information does not lead to unsafe decisions. Sensors also track the behavior of critical systems like hydraulics and flight controls, so technicians can perform maintenance before small issues become serious. Even when everything is working normally, sensors record data continuously, allowing airlines to analyze trends and anticipate wear. For passengers, this constant monitoring is invisible, but it is a key reason airplanes remain reliable. The aircraft is always watching itself to maintain safety, predictability, and a smooth flight experience. If one sensor fails, others take over automatically to maintain accurate information for pilots and onboard systems. Modern aircraft are built with multiple sensors for the same measurement, such as speed, altitude, or engine temperature. This redundancy ensures that if one sensor gives incorrect data or stops working, the other sensors continue providing reliable readings. The flight computer compares all inputs in real time and can disregard faulty signals without interrupting operations. Pilots are alerted to the failure, but can still rely on the remaining sensors to fly safely. This system prevents a single malfunction from affecting the aircraft's performance or safety. Passengers rarely notice when a sensor fails because the plane continues to operate smoothly. This automatic backup system adds a hidden layer of safety, showing how commercial airplanes are designed to handle small problems quietly and reliably while keeping the flight predictable and controlled. Airplanes can generate their own electricity in emergencies, which allows critical systems to keep working even if engines fail. Most commercial aircraft use generators powered by the engines, but they also have backup systems, including auxiliary power units, APUs, and batteries. In extreme cases, ram air turbines can deploy to provide electricity to essential controls. This power supports avionics, navigation, flight controls, communication, and instruments needed to land safely. Pilots train for situations where normal electrical sources are unavailable, so they know how to manage power efficiently. These systems are designed to switch automatically and operate without interruption. Passengers rarely notice these backups because they work silently in the background. Knowing that airplanes can generate their own electricity even during emergencies provides reassurance. It is one of many hidden layers of safety that make air travel predictable, controlled, and reliable, even in unlikely situations. Hydraulic systems power flight controls and landing gear, allowing pilots to move heavy surfaces with minimal physical effort. The ailerons, elevators, rudder, and flaps are all controlled using hydraulic pressure, which multiplies pilot input so adjustments are precise and smooth. Landing gear extension and retraction also rely on hydraulics because the wheels and supporting structures are heavy and require strong, controlled movement. Hydraulic fluid flows through pipes, pumps, and actuators to provide the necessary force. Systems are designed with redundancy, meaning multiple circuits can operate the same controls. If one hydraulic line fails, another can maintain operation. These systems are continuously monitored, and maintenance ensures that fluid levels, pressure, and components remain in safe condition. For passengers, the result is a smooth, responsive flight and reliable landings. Hydraulic systems are a quiet but essential technology that allows large, heavy aircraft to move accurately and safely. Multiple hydraulic systems operate independently to provide backup in case one system fails. Large aircraft often have 3 or more separate hydraulic circuits, each capable of controlling essential flight surfaces or landing gear. If one system loses pressure due to a leak or mechanical problem, the other systems continue to function normally. This redundancy ensures the plane can still maneuver, climb, descend, and land safely. Each system is monitored by sensors that alert pilots to any abnormal behavior, and maintenance crews check and service the systems regularly. Independent operation means a single failure cannot compromise the aircraft's critical functions. This design makes commercial airplanes extremely resilient. Passengers rarely notice these systems, but they play a crucial role in safety. The ability for hydraulic systems to back each other up quietly ensures that flights remain controlled, reliable, and predictable, even under rare or unexpected conditions. Airplane wings generate lift even at relatively low speeds, and this principle is critical for takeoff and landing. The shape of the wing, called an airfoil, is designed to create a difference in air pressure above and below it. Even when the plane is moving slowly during approach or after takeoff, the wings produce enough lift to keep the aircraft in the air. Engineers calculate wing size, shape, and angle to ensure it works reliably across all speeds the plane will encounter. Pilots also use flaps and slats, which extend parts of the wing to increase lift at low speeds, allowing for safer slow flight conditions. This design ensures that airplanes can climb safely after takeoff and descend smoothly for landing. For passengers, the lift generated quietly supports the aircraft's weight, providing a controlled and stable ride. Understanding this shows how airplanes remain airborne safely, even when speed is not very high. Takeoff speed is calculated precisely for each flight to ensure safety and efficiency. Factors like aircraft weight, runway length, weather, and wind direction all affect the speed needed for a safe liftoff. Pilots receive this information in advance and confirm it before starting the takeoff roll. If the plane is heavier, a higher speed is needed. If the runway is long or the wind is favorable, slightly lower speeds may be sufficient. These calculations are carefully reviewed, and followed exactly to make sure the airplane can become airborne safely. Autopilot and navigation systems rely on these speeds for climb and performance planning. Even small changes in weight or weather are considered. Passengers rarely notice these calculations, but they ensure that every takeoff is predictable, controlled, and within the aircraft's designed limits. Precise speed planning reduces stress on engines, wings, and landing gear while maximizing safety. Runways are designed longer than needed to provide safety margins during takeoff and landing. Engineers calculate the minimum runway length required based on aircraft type, weight, and typical weather conditions, then add extra length as a buffer. This allows pilots to accelerate safely, abort a takeoff if needed, or land even if braking conditions are less than ideal. The extra runway length also accounts for unexpected factors, such as wet or slippery surfaces, strong crosswinds, or slightly higher aircraft weight. Airports carefully maintain runways to ensure they remain smooth, level, and clear of debris. For passengers, this margin is invisible, but it provides an important layer of safety. Knowing that runways are longer than strictly necessary ensures that even if a takeoff or landing does not go perfectly, the aircraft has plenty of room to stop or continue safely. These extra measures make commercial flying extremely reliable. Brakes are capable of stopping the plane without engine assistance, and they are designed to handle the full weight and speed of the aircraft. Airplane brakes work on multiple wheels simultaneously and use hydraulic pressure to create strong friction against metal discs. This friction converts motion into heat, slowing the plane efficiently. Engineers design brakes to operate even if engines are not providing reverse thrust, and they test them under extreme conditions to ensure they can handle repeated use during landings. Pilots can apply brakes gradually or fully depending on runway length and conditions. Anti-skid systems prevent wheels from locking up, keeping the plane stable while slowing. Passengers rarely notice how powerful brakes are because the deceleration feels smooth and controlled. The design allows the aircraft to land safely even in emergencies, providing an extra layer of safety beyond engines or reverse thrust. Brakes are a critical component of predictable landings. Reverse thrust is helpful but not essential for stopping, and this is often misunderstood by passengers. Reverse thrust uses the jet engines to push air forward, slowing the plane after touchdown. While it can reduce the distance needed to stop, modern aircraft brakes alone are powerful enough to bring the airplane to a complete halt safely. Pilots use reverse thrust as a supplement, especially on shorter or wet runways, but it is not required for safety. Brakes, spoilers, and the friction of the tires on the runway do most of the work. Pilots are trained to land safely even if the engines cannot produce reverse thrust. This means that stopping the aircraft is not dependent on one system alone. Passengers may notice a stronger sensation when reverse thrust is used, but whether it is engaged or not, the landing remains predictable and controlled. The plane's design prioritizes redundancy and reliability to ensure safety. Pilots follow fixed landing procedures used worldwide to maintain consistency and safety across airports. These procedures include approach angles, speed adjustments, flap settings, and communication with air traffic control. Every pilot, regardless of airline or country, follows similar rules for each type of aircraft, which reduces errors and ensures predictability. Standardization also helps air traffic controllers coordinate multiple planes efficiently, keeping safe distances and preventing conflicts. Even in unusual conditions like crosswinds or turbulence, pilots apply these procedures systematically to maintain control. Checklists and step-by-step guidance ensure nothing is overlooked during approach and landing. Passengers rarely notice these exact procedures, but they provide structure for a safe, smooth touchdown. Following globally accepted standards allows pilots to respond to unexpected changes confidently and ensures that commercial aviation maintains high levels of safety everywhere in the world. Airports use lighting systems to guide aircraft at night or in low visibility, providing visual cues for pilots during approach and landing. Runways have edge lights, centerline lights, and touchdown zone lights that mark the safe path and boundaries. Approach lights extend from the runway to guide pilots from a distance, helping them align with the runway before descent. Taxiways, ramps, and aprons also use colored lights to prevent collisions on the ground. These systems are standardized internationally, so pilots can recognize and interpret them anywhere in the world. Lighting adjusts for weather conditions like fog or rain to maintain visibility. For passengers, the lights may seem like decoration, but they are critical for safety and precision. Pilots rely on these visual aids in combination with instruments to make landings accurate and controlled. The lighting systems allow flights to operate safely even after dark or in challenging conditions. Planes can land accurately even in low visibility because they rely on advanced navigation and landing systems. Instrument landing systems, ILS, GPS, and autopilot technology allow pilots to follow precise paths to the runway without needing to see it clearly. ILS provides guidance for both horizontal and vertical alignment, while autopilot can adjust speed, heading, and descent rate automatically. Pilots are trained to use these systems and to monitor instruments continuously, ready to take control if necessary. Airports support this with radio signals, ground-based sensors, and lighting to mark the runway. Even in fog, rain, or snow, commercial aircraft can make safe, precise landings. Passengers may feel cautious during these conditions, but the combination of technology, pilot training, and airport support ensures that landings remain predictable and controlled. Low visibility does not compromise safety due to these carefully coordinated systems. Autoland systems can land the aircraft automatically, and they are used when conditions make manual landings difficult, such as heavy fog, rain, or low visibility. These systems use radar, GPS, and instrument landing systems to guide the plane precisely to the runway, controlling speed, altitude, and alignment with incredible accuracy. Autoland monitors multiple parameters simultaneously, adjusting flaps, thrust, and braking as needed. Pilots supervise the landing and are ready to take over if necessary, but the system can complete the landing without human input. Airports equipped for Autoland have special signals and lighting to assist the process. The technology ensures that landings remain safe, predictable, and smooth, even when visual cues are minimal. Passengers may not notice that the plane landed automatically, but the system is designed to handle situations that would challenge human reaction times. Autoland is a quiet demonstration of the engineering that makes aviation reliable in all conditions. Many landings are smoother than pilots intend due to automation, and this is largely thanks to autopilot and flight control computers. These systems make tiny, rapid adjustments to speed, descent rate, and alignment that human hands cannot match perfectly. Even when pilots are controlling the landing manually, automated sensors assist by damping sudden movements caused by wind gusts or minor turbulence. Flaps and spoilers adjust automatically to optimize lift and drag for a softer touchdown. As a result, the plane can touch down with less jolting or bouncing than even the most experienced pilots could achieve alone. Passengers often notice these smooth landings and assume it is skill alone, but automation is quietly assisting. This combination of human skill and technology ensures that every landing is controlled, predictable, and comfortable, making commercial aviation safer and more relaxing than many people realize. Aircraft cabins are designed to reduce engine noise, creating a calmer environment for passengers. Engineers use insulation, soundproofing panels, and vibration dampers to minimize the noise that enters the cabin from engines and airflow. Engines themselves are designed with noise reduction features like chevrons on the exhaust and specially shaped fan blades. The cabin layout, including walls, ceilings, and flooring, is optimized to absorb and block sound while keeping weight low. Air circulation systems are also designed to operate quietly. This combination of engineering efforts ensures that, even during takeoff and high-speed cruise, noise levels remain low enough for conversation, reading, or relaxation. Passengers often only hear a steady hum rather than loud engine sounds. The careful design of the cabin and engines allows flights to feel more comfortable and calm, showing how engineering balances performance, safety, and passenger comfort. The steady hum in flight is a sign of stable engine operation and consistent airflow over the aircraft. This continuous sound comes from jet engines running at a constant speed, while the aircraft cruises at high altitude. Engine components like fans, compressors, and turbines rotate smoothly and produce a predictable noise frequency. This hum indicates that the engines are functioning within normal limits, without sudden changes or disruptions. Pilots monitor engine instruments to ensure the power output, temperature, and fuel flow remain steady. Passengers may find this background hum soothing, even subconsciously, because it signals that the aircraft is performing reliably. Unlike abrupt noises, which could indicate a problem, the even sound reassures both crew and passengers that systems are stable. The hum is more than just a sound. It reflects the careful design, testing, and monitoring that keeps modern flights predictable, safe, and smooth. Vibration levels are carefully monitored during flight to ensure passenger comfort and aircraft safety. Sensors on the engines, wings, and fuselage continuously detect unusual vibrations caused by turbulence, engine performance, or structural movement. Pilots and onboard systems use this information to adjust engine power, flight speed, or altitude to reduce vibrations when possible. Engineers also review this data after flights to detect early signs of wear or imbalance in engines or other components. Excessive vibrations are rare, but could indicate potential mechanical issues if not addressed. Passengers usually only feel mild shaking during turbulence, but the aircraft's design and monitoring systems work to minimize even minor vibrations. Knowing that every movement is tracked highlights the level of control built into commercial aviation. Careful monitoring ensures that the plane operates smoothly, components last longer, and passengers experience a quiet and comfortable flight even at high speeds and altitudes. Seats are attached to structures tested for extreme forces to keep passengers safe during emergencies. Every seat and its mounting hardware must pass rigorous tests, including high-impact simulations that exceed what would normally occur in a crash or sudden stop. Engineers design seat tracks, bolts, and frames to remain secure even under extreme stress. Safety belts are also part of this system, holding passengers in place and distributing force evenly across the body. Regular maintenance checks ensure that no bolts are loose and that the seats remain firmly attached. The design accounts for all passenger sizes and weights. Passengers rarely notice how robust these attachments are, but they are critical in protecting lives during unexpected events. This careful engineering means that seats do not detach or fail, providing a predictable and controlled safety feature that quietly supports every flight, giving confidence in both normal and emergency situations. Overhead bins are designed to handle heavy loads and remain secure, even in turbulence or hard landings. Each bin has weight limits and locking mechanisms tested far beyond what is typically stored by passengers. Engineers design the bins with strong materials and reinforced hinges so that doors do not pop open accidentally. During certification, bins are loaded with weights and subjected to vibration and motion tests to ensure they can handle stress safely. Passengers often store luggage without realizing the careful engineering involved. Cabin crew also check bins to make sure items are placed safely before takeoff. Properly designed overhead bins reduce the risk of objects falling and injuring passengers during flight. These simple-looking storage spaces are an important part of the airplane's overall safety system. By securely containing luggage, bins contribute to a controlled and predictable environment inside the cabin. Cabin crew are trained primarily for safety, not service, even though passengers often see them delivering food and drinks. Flight attendants learn emergency procedures, evacuation protocols, firefighting, first aid, and security measures long before practicing meal service. They are responsible for guiding passengers during emergencies, using equipment like slides, oxygen masks, and fire extinguishers. Crew members rehearse evacuation drills regularly and are trained to remain calm under pressure, ensuring passengers follow instructions quickly and safely. Serving food or drinks is secondary to their main role of keeping everyone alive and protected. This safety-first training is what allows crews to handle rare but serious events efficiently, such as medical emergencies or mechanical problems. Passengers may feel reassured by the crew's presence, but the real expertise lies in safety knowledge. Their readiness ensures that flights remain controlled, safe, and predictable under all circumstances. Emergency equipment is checked before every flight to ensure it is ready if needed. This includes life vests, fire extinguishers, first aid kits, oxygen systems, and emergency slides. Cabin crew and ground staff follow detailed checklists to verify that each item is present, functional, and correctly stored. Even small things, like ensuring the seals on fire extinguishers are intact or the oxygen canisters are full, are inspected. These checks happen quietly before passengers board, but they are critical to flight safety. Airlines follow strict regulations that require documentation of every inspection, and maintenance crews perform additional checks during regular aircraft servicing. Passengers rarely notice these preparations, but if an emergency occurs, this equipment can make the difference between life and serious injury. This routine, invisible work is part of the reason commercial aviation is one of the safest ways to travel. Every flight begins with these safety systems confirmed and ready. Oxygen masks supply breathable air for several minutes in case of sudden cabin depressurization. If the cabin loses pressure at high altitudes, the oxygen level drops rapidly, making breathing difficult. Masks automatically deploy from overhead compartments, and passengers are instructed to pull them down to start the flow of oxygen. The supply is designed to last long enough for the plane to descend to a safer, lower altitude where air pressure is sufficient for normal breathing. Pilots are trained to respond immediately, reducing altitude quickly and safely while ensuring passengers have time to breathe normally. These masks are tested rigorously to confirm the oxygen flow rate and duration. Passengers may rarely use them, but they are a critical part of cabin safety. The system ensures that even in emergencies, the aircraft environment remains survivable, predictable, and controlled while the plane descends safely. Planes are designed to descend safely during depressurization, which is when the cabin loses air pressure at high altitude. If this happens, pilots initiate an emergency descent to reach an altitude where passengers can breathe normally, usually below 10,000 feet. The aircraft's structure, engines, and control systems are engineered to handle rapid descent safely without overstressing the airframe. Pilots follow procedures that balance speed, angle of descent, and navigation to reach a safe altitude efficiently while avoiding other air traffic. Oxygen masks provide passengers with air during the descent, giving them enough time to breathe comfortably. Even in rare depressurization events, commercial aircraft are capable of controlled, stable descent without putting passengers at unnecessary risk. These safety systems, combined with pilot training, ensure that the flight remains predictable, orderly, and safe despite sudden changes in cabin pressure. Doors cannot be opened while the cabin is pressurized because the pressure difference between the inside and outside is extremely high. At cruising altitude, the outside air pressure is much lower than inside the cabin. This difference creates a force that pushes the door inward or outward with thousands of pounds of pressure, making it impossible for anyone to open. Doors are engineered with multiple latches and locking mechanisms that engage automatically when pressurization is active. Only after the plane descends and cabin pressure equals outside pressure can the doors be safely opened. This design prevents accidental openings during flight and ensures that the cabin remains sealed and safe. Passengers may not realize this, but it is a critical safety feature that keeps everyone secure at high altitudes. Understanding this explains why flying at thousands of feet is safe even though the doors are technically large openings. The shape of an airplane nose reduces drag, allowing the plane to move efficiently through the air. The nose is designed to be smooth and aerodynamic, minimizing resistance as the aircraft pushes forward at high speeds. A well-shaped nose decreases turbulence and allows air to flow over the fuselage and wings more smoothly. This improves fuel efficiency and reduces engine strain, which is especially important during long flights. Pilots and engineers carefully design the nose for each type of aircraft to balance performance, safety, and cabin space. Even small changes in shape can affect how the plane handles and consumes fuel. Passengers may not notice the design, but it plays a critical role in keeping the flight stable and energy efficient. The nose is also designed to withstand bird strikes and minor debris impacts, combining safety and performance. This quiet, precise engineering ensures the airplane moves through the sky predictably and efficiently. Aircraft paint helps protect the structure from corrosion, which can weaken metal over time. Airplanes are exposed to rain, humidity, salt in coastal areas, and other environmental factors that can damage the fuselage and wings. The paint acts as a barrier, preventing moisture and chemicals from reaching the underlying metal. Engineers choose specific types of paint that are lightweight, durable, and resistant to cracking or peeling. Layers of paint are applied carefully during manufacturing and maintenance, with inspections to ensure coverage remains intact. Passengers often notice the bright colors and airline logos, but the paint's main job is protection, not decoration. Maintaining the paint ensures that the aircraft remains strong, reduces long-term maintenance costs, and keeps the plane safe throughout its operational life. This invisible layer of protection quietly contributes to the predictability and reliability of every flight. Planes are washed to remove dirt, grease, and other debris that affect efficiency and safety. Dirt can build up on the fuselage, wings, and engine inlets, slightly increasing drag and reducing fuel efficiency. Even small particles can impact airflow over the wings, affecting lift and overall performance. Regular washing removes these contaminants and allows maintenance teams to inspect the aircraft for corrosion, cracks, or damage more easily. Specialized cleaning methods use water, detergents, and soft brushes to protect sensitive surfaces like windows and antennas. Passengers rarely notice this routine, but it directly affects the plane's ability to operate smoothly and efficiently. Airlines schedule washes based on usage, weather, and environmental exposure. Clean surfaces reduce fuel consumption, improve aerodynamics, and help the aircraft perform predictably. Routine washing is a simple but important maintenance step that keeps flights safe, efficient, and controlled. Navigation systems calculate the aircraft's position multiple times per second to keep it on course accurately. Modern planes use GPS, inertial navigation, and other sensors to determine latitude, longitude, altitude, and speed in real time. The onboard computer continuously compares this data with the planned route, making small adjustments to heading, speed, or altitude as necessary. Even when the autopilot is not engaged, pilots monitor these systems to confirm the plane remains on the intended path. Frequent updates allow for precise turns, climbs, and descents, ensuring the flight is efficient and predictable. Airports, air traffic control, and onboard instruments also rely on this constant positioning information. Passengers may not notice, but this rapid, repeated calculation is why planes can navigate accurately over long distances, oceans, and complex airspace. It is a hidden layer of precision that keeps flights controlled and safe. Aircraft clocks are synchronized with global time standards to ensure accurate coordination between pilots, air traffic control, and flight operations. Every airplane operates in different time zones and must communicate precisely about departure, arrival, and navigation timing. Synchronized clocks help pilots file accurate flight plans, report positions, and maintain separation from other aircraft. They also support automated systems like autopilot and navigation, which rely on precise timing to calculate position and speed. Even small errors in timing could lead to confusion or delays. Airlines and air traffic controllers continuously monitor these systems to maintain accuracy. Passengers may not notice, but synchronized clocks allow flights to operate smoothly across continents and oceans, ensuring connections and schedules remain predictable. This precise timing is part of the invisible framework that keeps aviation organized, safe, and efficient, showing how even small details are crucial for global air travel reliability. Most modern planes share flight data with manufacturers in real time or after landing. This information includes engine performance, control inputs, system alerts, and environmental conditions. Manufacturers analyze the data to detect potential issues early, improving safety and reliability. Airlines receive insights on how specific aircraft perform, allowing adjustments to maintenance schedules and operational procedures. Data sharing also helps engineers develop upgrades or modifications to improve efficiency and comfort. Even minor patterns, like small vibrations or temperature variations, can be tracked to prevent bigger problems later. Pilots and passengers rarely see this process, but it strengthens safety because experts can monitor trends across many flights and aircraft worldwide. Continuous analysis helps ensure predictable performance, smooth operations, and reduced chances of unexpected failures. This hidden feedback loop is a major reason why modern aviation is highly reliable, efficient, and controlled. Maintenance schedules are adjusted using real flight data to ensure aircraft remain safe and efficient. Instead of relying only on standard intervals, Engineers analyze information from each flight, including engine hours, takeoffs, landings, and environmental conditions. If a component experiences more stress than usual, its inspection or replacement can be scheduled sooner. Conversely, parts that show minimal wear may continue operating safely for longer. This approach, called condition-based maintenance, ensures that resources are used efficiently while maintaining safety. Airlines monitor trends from multiple aircraft to identify patterns and prevent potential issues before they become serious. Passengers rarely notice, but this data-driven maintenance keeps planes operating predictably and reduces the risk of unexpected delays or mechanical problems. By using real-time information, aircraft remain reliable, comfortable, and safe throughout their service life. Aircraft manuals are updated continuously to reflect new procedures, safety improvements, and system modifications. Pilots and maintenance crews rely on these manuals for instructions on operating and servicing every part of the airplane. Updates may include changes to navigation systems, engine operation, or emergency procedures based on manufacturer recommendations or regulatory guidance. Manuals also incorporate lessons learned from incidents, testing, and real-world experience, ensuring crews always have the most current information. Airlines distribute updated manuals digitally or in print, and crews are trained to follow the latest procedures. Passengers do not see this process, but it ensures that flights are operated using verified, precise, and safe practices. Continuous updates maintain predictability, allowing pilots and technicians to respond correctly to any situation. These manuals are a quiet, essential tool that supports controlled, efficient, and safe air travel. Safety improvements are shared internationally to make aviation safer for everyone. When engineers, airlines, and regulators discover a better way to handle emergencies, prevent mechanical problems, or improve procedures, this information is communicated to other countries and airlines. Organizations like the International Civil Aviation Organization, ICAO, ensure that safety lessons from one part of the world benefit all flights globally. This cooperation helps reduce accidents, standardizes best practices, and creates consistent safety standards no matter where you fly. Even small changes like improved cockpit checklists or better fire suppression systems are shared widely. Passengers rarely see this process, but it is a critical part of why commercial aviation remains one of the safest modes of transport. By learning from every incident and improvement, the industry keeps flights predictable, controlled, and safe worldwide. Airlines rarely keep safety procedures secret because transparency improves overall flight safety. Pilots, cabin crew, engineers, and regulators all need access to the latest protocols to operate aircraft reliably. Sharing information ensures that everyone follows the same procedures for emergencies, maintenance, and operations. While some technical details, like proprietary system designs, are protected, the actual safety instructions are widely distributed to qualified personnel. This openness allows training programs to be standardized and ensures that crews are prepared for the same scenarios no matter where they work. Passengers may not notice, but it means that airlines follow globally accepted rules and are accountable for predictable, controlled, and safe operations. Safety knowledge is treated as public within the industry to prevent mistakes, improve performance, and protect lives. Airplanes are designed to handle lightning strikes safely, which is important because thousands of commercial flights encounter lightning each year. Engineers use conductive materials like aluminum and special coatings to allow electricity to flow around the plane without damaging critical systems. Lightning usually hits the nose, wings, or tail, travels along the aircraft's skin and exits without harming passengers or engines. Aircraft electronics are shielded and grounded to prevent malfunctions during strikes. Pilots are trained to react calmly, maintain course, and continue the flight without emergency procedures unless unusual effects occur. Every lightning strike is logged and analyzed to improve designs further. Passengers may feel a slight flash or hear a sound, but the plane continues flying safely. The design and testing of airplanes for lightning show how aviation anticipates natural hazards and ensures that flights remain controlled, predictable, and secure. Lightning usually passes through the aircraft without damage because of careful engineering and protective design. The airplane's outer skin, often made of aluminum or composite materials with conductive layers, directs electrical current safely along its surface. Internal systems like avionics, engines, and fuel systems are shielded to prevent sparks or shorts. Pilots follow standard procedures but rarely need to take emergency actions because the plane continues functioning normally. Even if a strike occurs, sensors and inspections ensure that any minor effects are detected and repaired during maintenance. Passengers might hear a snap or see a flash outside the window, but the plane's systems keep operating predictably and safely. This ability to handle lightning is tested repeatedly during certification, so aircraft can safely fly through storms. Understanding this invisible protection demonstrates the careful engineering that allows air travel to remain safe, controlled, and reliable under natural hazards. Static wicks on wings discharge electrical buildup that naturally occurs during flight. As an airplane moves through the air, friction with particles, moisture, and atmospheric electricity can cause a small electrical charge to accumulate on the aircraft. Static wicks are thin, rod-like devices attached to the trailing edges of wings, tail, and control surfaces. They safely release this electrical energy into the atmosphere, preventing interference with onboard radios, navigation systems, and communication equipment. Without static wicks, accumulated charge could create sparks or static noise, affecting instruments and making communications less clear. Pilots and passengers usually do not notice static wicks working, but they are essential for keeping flight systems reliable. The wicks allow airplanes to operate safely even in electrically charged clouds or near thunderstorms. This quiet, simple feature is an example of invisible engineering that ensures predictable, controlled, and safe flights in all conditions. Planes are tested in artificial lightning environments during development to make sure they can handle real strikes safely. Engineers simulate lightning using high-voltage equipment to strike sections of the aircraft, while monitoring how electricity travels through the structure and affects onboard systems. These tests check that the conductive skin, wiring, avionics, and fuel systems remain protected. Any weak points are reinforced or redesigned before the plane enters service. Testing includes multiple strike scenarios, such as hits to the nose, wings, or tail, as well as simultaneous strikes. Pilots and maintenance crews are trained to inspect planes after actual lightning events. Passengers may never notice, but these rigorous tests ensure that real lightning strikes will pass safely over the aircraft without disrupting flight operations. This testing process is another layer of safety that makes air travel controlled, reliable, and predictable even in thunderstorms. Ice protection systems prevent wing icing, which is critical because ice can change the shape of the wing and reduce lift. Ice forms when flying through clouds with supercooled water droplets, especially in cold temperatures. Aircraft use systems like inflatable boots, chemical dacers, and heating elements to stop ice from forming or remove it quickly. Sensors detect the presence of ice and automatically activate these systems. By keeping the wings and control surfaces free of ice, the plane maintains normal lift, stability, and control. Pilots monitor ice alerts and follow procedures to activate or adjust anti-icing systems if needed. Passengers rarely notice this, but it is vital for flight safety. Without ice protection, even small accumulations could make takeoffs, climbs, or turns risky. The technology ensures that airplanes operate safely in cold, cloudy conditions, maintaining predictable and controlled flight. Heated surfaces melt ice during flight, ensuring the airplane remains safe and controllable in cold weather. Leading edges of wings, tail surfaces, engine inlets, and sometimes propellers use electrical heating or bleed air from engines to raise temperatures above freezing. This prevents ice from forming or removes it immediately if it begins to accumulate. Maintaining smooth, ice-free surfaces is crucial for lift, drag, and control of the aircraft. Pilots monitor ice detection systems and activate heaters automatically or manually as needed. Passengers do not see this system working, but it allows planes to fly through freezing clouds without losing performance. Engineers test these heating systems extensively to ensure they operate under extreme cold and pressure. The combination of sensors and heated surfaces is a hidden safety feature that keeps flights predictable, reliable, and controlled, even in harsh winter conditions or high-altitude clouds. Sensors detect ice formation early to prevent dangerous situations during flight. Modern aircraft are equipped with ice detectors on wings, tail surfaces, and sometimes engines. These sensors monitor temperature, moisture, and the presence of ice crystals. If ice begins forming, the sensors send immediate signals to the aircraft's anti-icing or de-icing systems. Early detection is critical because even small ice accumulations can affect lift, drag, and control. Pilots are alerted automatically, allowing them to activate heating elements, boots, or chemical sprays before the ice becomes significant. By catching icing early, the airplane maintains stability and safety. Passengers may never notice, but this technology works quietly in the background. It ensures predictable flight performance in freezing conditions and helps avoid emergency situations. Sensors provide continuous monitoring, so the aircraft is always ready to respond to ice, keeping operations controlled, smooth, and safe in all weather conditions. Pilots receive alerts before ice becomes a problem, giving them time to respond without rushing. When sensors detect ice accumulation, cockpit systems trigger visual or auditory warnings. Pilots can then engage anti-icing or de-icing systems, adjust speed, or change altitude to reduce ice formation. This early warning ensures that lift, drag, and stability are maintained throughout the flight. Training programs prepare pilots to recognize and act on these alerts efficiently. Because of these systems, most icing events are handled automatically or with minimal manual input. Passengers usually notice nothing unusual during these situations. The combination of sensors and pilot awareness ensures that flights remain predictable and controlled, even in challenging weather. By receiving timely alerts, pilots can prevent ice from affecting flight performance, demonstrating how modern aviation relies on technology to maintain safety and smooth operation. Aircraft systems prioritize stability over speed to ensure safe and predictable flight. While airplanes can travel very fast, maintaining steady, controlled movement is more important than reaching maximum speed at all times. Flight computers, autopilot, and stability augmentation systems constantly monitor attitude, roll, pitch, and altitude to prevent sudden or extreme movements. Even when turbulence or wind gusts occur, These systems adjust control surfaces automatically to keep the plane level and comfortable. Pilots rely on this prioritization to reduce stress on the aircraft structure and maintain safe handling. Passengers may notice the gentle, controlled motion rather than abrupt changes. By focusing on stability, airplanes remain reliable, responsive, and safe during all phases of flight. Smooth, steady operation also improves fuel efficiency and reduces wear on engines and wings, showing why stability is more important than raw speed. Smooth flight is more efficient than fast flight because it reduces drag and fuel consumption. When airplanes climb, descend, or cruise steadily without abrupt changes, airflow over the wings and fuselage remains optimal. Sudden accelerations or turbulence can increase resistance, forcing engines to work harder and use more fuel. Autopilot and flight management systems maintain smooth flight paths, adjusting minor speed and altitude changes to maximize efficiency. Pilots plan routes and altitudes to minimize unnecessary maneuvers, taking advantage of tailwinds and avoiding turbulent areas. Passengers often notice the calm, steady movement rather than rapid changes, which also makes the journey more comfortable. Smooth flight not only conserves fuel, but also reduces stress on the aircraft structure, engines, and systems. Predictable, controlled motion ensures that every flight is safe, reliable, and energy efficient, demonstrating how careful planning and technology improve overall performance. Most flight delays are caused by ground operations, not problems with the aircraft itself. Tasks such as refueling, catering, luggage loading, and passenger boarding often take longer than expected. Weather conditions can also slow down airport operations even if the plane is ready to fly. Air traffic control may delay takeoff or landing due to congestion, or to maintain safe distances between planes. Airlines carefully monitor these factors to minimize delays, but some things like traffic or mechanical inspections are unavoidable. Pilots usually have a fully functional plane and are ready to fly, meaning the aircraft itself is rarely the reason for delays. Passengers often blame weather or scheduling, but the majority of delays happen on the ground. Understanding this shows that air travel is carefully coordinated, and delays are often part of ensuring safe, organized, and predictable operations before the plane even leaves the runway. Aircraft spend more time on the ground than in the air, even though passengers mostly think about the flight itself. Between arrivals and departures, airplanes undergo refueling, cleaning, maintenance checks, and loading of passengers and cargo. Turnaround time varies by aircraft size and airport, sometimes taking just 30 minutes for small jets or several hours for wide-body planes. Ground staff coordinate these activities to keep flights on schedule and ensure everything is ready for takeoff. Airlines also perform routine inspections and minor repairs while the aircraft is on the ground. Even if a plane is in the air for 10 hours, it may spend longer preparing and servicing between flights. Passengers rarely notice this behind-the-scenes activity, but it is essential for safety and reliability. Ground operations ensure that each flight is controlled, predictable, and ready to operate efficiently. Engines cool gradually after shutdown to prevent damage to critical components. Jet engines operate at extremely high temperatures during flight, and sudden cooling can cause metal parts to warp, crack, or wear unevenly. After landing, engineers follow procedures that allow engines to cool slowly while monitoring temperature and performance. Auxiliary power units, APUs, may continue running to provide electricity, cabin air, and hydraulic pressure while the engines settle. Gradual cooling also allows for easier inspection of components, making it possible to identify wear, leaks, or other issues. Passengers rarely notice, but this slow cooldown is a key part of keeping engines reliable for the next flight. The process ensures predictable performance, reduces maintenance issues, and prolongs engine life, making commercial aviation safer, efficient, and consistent across repeated operations. Aircraft components are tagged and tracked individually to ensure safety and reliability. Every part, from engines to seat bolts, has a unique identification number recorded in maintenance logs. When a component is installed, inspected, repaired, or replaced, this information is updated to maintain a complete history. Tracking helps airlines comply with safety regulations, schedule maintenance, and replace parts before they fail. It also allows engineers to identify trends, such as which parts wear faster under certain conditions, and adjust procedures or design accordingly. If a component recalls or safety alert is issued, the airline can locate it immediately. Passengers rarely see this system at work, but it ensures that every flight operates predictably and safely. Detailed tracking of individual components is a critical behind-the-scenes measure that supports controlled, reliable, and safe air travel worldwide. Even small parts have serial numbers to maintain complete traceability and safety. Bolts, sensors, landing gear components, and even tiny electrical connectors are assigned unique identifiers. When a part is installed, repaired, or inspected, its history is logged in the aircraft's maintenance records. This tracking ensures that every component meets safety standards, allows airlines to replace worn or faulty parts before they fail, and helps engineers analyze performance trends across many flights. If a part develops a defect, the serial number allows it to be traced to other aircraft, preventing potential issues from spreading. Passengers rarely see the importance of these tiny details, but they contribute to predictable and controlled operations. By knowing the history of each part, airlines can maintain high reliability and safety standards. Even the smallest components are part of the intricate system that keeps air travel smooth, efficient, and secure. Planes can operate safely in extreme temperatures, from the freezing cold of high altitudes to scorching heat at desert airports. Aircraft engines, hydraulics, and avionics are designed to withstand temperature extremes without losing performance or safety. Materials used in the fuselage, wings, and control surfaces expand and contract predictably, ensuring structural integrity. Pilots adjust procedures depending on temperature, including engine settings, takeoff distances, and fuel calculations. Cooling and heating systems inside the cabin maintain a comfortable environment for passengers and crew, even if outside conditions are harsh. Extreme weather testing during aircraft certification ensures that all systems operate safely under these conditions. Passengers may notice a very cold or hot day, but the plane remains fully capable of flying safely. This resilience demonstrates careful engineering and planning, allowing flights to remain predictable, controlled, and reliable in nearly any climate on Earth. Aircraft are designed to fly safely for decades, with some planes serving 20 to 30 years or more. The fuselage, wings, engines, and systems are built to handle repeated stress from takeoffs, landings, turbulence, and pressurization cycles. Materials are chosen for strength, durability, and resistance to corrosion, while critical components undergo regular inspections and replacement schedules. Engines, electronics, and hydraulics are updated or overhauled to extend service life. Airlines track flight hours, cycles, and maintenance history to ensure every plane remains safe throughout its career. Even older planes continue to operate predictably because of this structured monitoring and maintenance. Passengers rarely notice the age of an aircraft, but engineering and careful upkeep allow decades of safe, controlled, and efficient service. This longevity reflects the combination of design, materials, and attention to detail in modern aviation. Retired airplanes are often dismantled carefully to recover valuable parts and materials. Engines, avionics, landing gear, and control surfaces are removed, inspected, and refurbished for use in other planes. Aluminum, composites, and other materials are recycled to reduce waste and environmental impact. Aircraft interiors like seats and panels are repurposed or recycled. Dismantling follows strict procedures to ensure safety and prevent damage to reusable components. Even after retirement, parts of the airplane continue to support other aircraft, extending the life cycle of expensive and critical systems. Passengers may never think about this process, but it reflects the attention to efficiency and sustainability in aviation. Carefully dismantling aircraft ensures that resources are reused, maintenance is cost-effective, and retired planes continue to contribute to safe and controlled operations across the industry. Many aircraft parts are reused or recycled after their original service, which helps reduce costs and environmental impact. Components like engines, landing gear, avionics, and flight instruments are inspected, refurbished, and certified for use in other airplanes. Materials such as aluminum, titanium, and composites are recycled to make new parts or sold for other industries. Even seats, panels, and interior fittings can be repurposed or converted into furniture or industrial items. Recycling and reusing parts require careful procedures to ensure that safety and performance are never compromised. Each reused part has a detailed maintenance and inspection history, so it continues to perform predictably. Passengers rarely see this behind-the-scenes activity, but it helps airlines maintain efficiency while keeping flights safe. The practice of reusing and recycling components shows how aviation combines technology, cost management, and environmental responsibility without compromising controlled and reliable flight. Aviation safety improves incrementally, not suddenly, meaning small changes over time make flying increasingly reliable. Engineers, regulators, and airlines continuously analyze flight data, incidents, and maintenance records to find areas for improvement. New technologies, design upgrades, training methods, and operational procedures are introduced gradually, tested, and integrated into the system. Even minor changes like improved cockpit displays or enhanced sensor accuracy add layers of protection. Passengers rarely notice these updates, but each step builds a more predictable and controlled aviation environment. The aviation industry learns from every flight, incident, and research study, slowly reducing risks and increasing safety margins. This steady, incremental approach ensures that flying becomes safer year after year. It is why modern air travel has an extraordinary safety record, and why passengers can trust that every system, from engines to training procedures, is continuously improving. Flying is statistically safer than most daily activities, including driving or walking in busy streets. Aviation has rigorous safety standards, redundant systems, and highly trained personnel, making accidents extremely rare. Every flight undergoes extensive planning, from weather assessment to fuel calculations and route selection. Aircraft are maintained, inspected, and monitored constantly, and pilots train regularly for both routine and emergency scenarios. Global aviation regulations ensure that airlines and airports follow strict protocols to prevent incidents. Redundant engines, backup systems, and advanced navigation technologies further reduce risk. While passengers may feel nervous due to height or speed, the actual probability of an accident is extremely low. Safety statistics show that flying thousands of miles is often safer than everyday tasks such as commuting by car. Understanding this helps passengers feel calm and confident, knowing that flights are predictable, controlled, and designed with multiple layers of protection. Safety improvements are often invisible to passengers, meaning that the systems protecting them operate quietly in the background. Features like redundant hydraulics, autopilot stability control, lightning protection, de-icing systems, and advanced sensors are all active without drawing attention. Pilots and maintenance crews monitor these systems continuously, ensuring everything functions correctly. Even the design of the fuselage, wings, and engines incorporates invisible safety measures, like stress testing, corrosion protection, and structural reinforcements. Cabin crew follow extensive safety protocols that passengers rarely see, and data from each flight is analyzed for potential improvements. While passengers focus on comfort, service, or scenery, aviation professionals are constantly applying innovations to maintain predictable, controlled, and safe flight. The invisible nature of these improvements shows how much engineering, planning, and monitoring work together to make flying one of the safest modes of transportation, where the majority of protective measures are operating silently and efficiently behind the scenes. The goal of aviation is consistency, not excitement. Every design, procedure, and operation focuses on predictable performance rather than thrills. Engineers create aircraft that behave the same way every time, regardless of weather, load, or altitude. Flight paths, autopilot systems, and control responses are carefully tested to ensure that a plane reacts as expected under any circumstance. Pilots follow strict protocols that prioritize steady performance over sudden maneuvers or speed. Passengers often assume flying is exciting because of speed and altitude, but the real focus behind the scenes is on repeatable, reliable behavior. By prioritizing consistency, aviation reduces risk, ensures safe operations, and allows crews to handle emergencies calmly. Every adjustment, check, and system function is designed to make the flight predictable. This emphasis on reliability explains why most flights are safe, smooth, and controlled, even when passengers feel nervous about being thousands of feet in the air. Most flights are uneventful by design because the aviation system is built to prevent surprises. Routes are planned carefully, weather is monitored continuously, and air traffic control maintains safe separation between airplanes. Pilots follow standardized procedures, and aircraft are equipped with multiple redundant systems to handle potential failures without affecting passengers. Even turbulence is often minor and managed through altitude adjustments or autopilot control. Passengers may notice little more than the steady hum of engines or slight movement from bumps, which is entirely normal. This uneventful nature is intentional. Every aspect of the flight, from takeoff to landing, is planned to be predictable and controlled. By designing flights to be routine, engineers and pilots reduce stress on both people and machines. The quiet, uneventful experience is actually a sign of successful planning and safety, showing how aviation operates reliably behind the scenes to keep passengers secure and comfortable. Pilots aim to make flights feel boring because calm, routine operations are safer than dramatic or sudden actions. Smooth climbs, steady cruising, and gradual descents prevent stress on the aircraft structure, engines, and systems. Boring flights mean that instruments remain within normal limits and unexpected situations are minimized. Pilots follow checklists and standard procedures precisely, reducing the chance of mistakes. When passengers notice little more than stable motion and regular engine noise, it reflects successful operation and safety. Even during turbulence or minor system adjustments, pilots prioritize predictable handling and comfort. Boring flights are a sign that every system, autopilot, navigation, hydraulics, and engines, is performing correctly. By keeping the flight uneventful, pilots ensure predictable, controlled, and safe operations. Passengers may enjoy views or entertainment, but the behind-the-scenes goal is always to make the journey smooth, quiet, and reliable, minimizing risk and maximizing safety. Calm procedures reduce human error because predictable, step-by-step routines give pilots and crew clear guidance during every phase of flight. Checklists, standard operating procedures, and automated systems limit mistakes caused by distraction, stress, or unusual situations. Pilots practice emergency drills repeatedly so that their responses become automatic, allowing them to act calmly under pressure. Even during turbulence, system alerts, or unexpected events, following calm procedures ensures the plane remains stable and controlled. Cabin crew also follow structured routines for safety checks, passenger instructions, and equipment use. By emphasizing calm, methodical operations, aviation reduces the impact of human error, which is one of the main risks in transportation. Passengers may never notice these routines, but their consistent application ensures that flights are predictable, safe, and controlled. Calm procedures are a key reason why air travel has such a strong safety record, despite complex systems and variable conditions. Repetition in aviation increases reliability because performing the same tasks the same way creates predictability and reduces mistakes. Pilots follow standard procedures for takeoff, cruising, and landing every day, even across different aircraft. Maintenance crews inspect planes using the same step-by-step checklists repeatedly, ensuring nothing is overlooked. Even automated systems operate on consistent algorithms that manage speed, altitude, and stability without variation. This repetition means that both humans and machines behave in a predictable, controlled manner, making errors less likely. When unusual situations occur, crews rely on repeated training and familiar routines to respond calmly and effectively. Passengers may not notice the repeated actions behind the scenes, but it is a crucial reason why aviation is highly safe. Repetition creates a rhythm in operations, ensures components are handled correctly, and builds trust in every flight. It is this predictable, controlled repetition that allows millions of people to fly safely every day. 98. Airplanes succeed because they avoid surprises, not because they perform extraordinary feats. The design, procedures, and operations aim to make every flight predictable. Pilots plan routes carefully, check weather conditions, and rely on autopilot systems to maintain steady flight. Air traffic control monitors planes constantly, ensuring safe separation and anticipating changes. Aircraft systems have redundancy, meaning backup components take over automatically if something fails. Emergency drills and simulations prepare pilots for rare events so that even unexpected situations are handled calmly. Passengers may notice little more than steady motion and quiet engines, which reflects the system working perfectly. By focusing on avoiding surprises, aviation ensures that every flight remains safe, smooth, and controlled. Predictability is the key to success, showing that the calm, uneventful nature of commercial aviation is the result of careful planning, technology, and continuous preparation. 99. Quiet, routine flights are the intended outcome because safe air travel depends on predictability. Every part of aviation, from aircraft design to pilot training, from maintenance to navigation, is built to make flights steady and controlled. Autopilot systems keep the plane level and on course, while redundant engines and hydraulics handle failures silently. Pilots follow detailed procedures to maintain stability, and air traffic controllers manage traffic in a structured, orderly way. Even turbulence, which might feel alarming, is rarely dangerous and is addressed through altitude changes or autopilot adjustments. Passengers may feel that a flight is calm or uneventful, but this is intentional and reflects successful operation. Routine flights minimize stress on passengers, pilots, and the aircraft itself while maximizing efficiency and safety. By designing for quiet, predictable operations, aviation ensures that flights remain controlled, reliable, and consistently safe. This routine is not boring. It is evidence of careful engineering and planning. 100. The most relaxing thing about airplanes is how rarely anything unexpected happens, despite flying thousands of feet above the ground at high speeds. Pilots, engineers, and air traffic controllers work together to manage every detail, from fuel and weather to navigation and safety systems. Redundant engines, autopilot, de-icing, and lightning protection all operate quietly in the background to prevent surprises. Passengers may notice minor bumps or the hum of engines, but these are normal, controlled aspects of flight. Emergencies are extremely rare, and the vast majority of flights reach their destination safely without any issue. The invisible planning, repeated procedures, and monitoring systems ensure that airplanes remain predictable and controlled throughout the journey. This reliability allows passengers to relax, enjoy views or entertainment, and trust the journey even at extreme altitudes. The calm, uneventful experience is not by chance. It is the result of careful design, training, and preparation that makes flying one of the safest, most dependable modes of transport.